Hey guys, this is Miss Mo. We're still on 2.2. The next thing we're going to talk about equal sets. Equal sets are what you think they are. They have the same amount of elements, as in there's 5 in this one and there's 5 in the other. And the elements in both sets are the same, as in ABCD is in one set and ABCD is in the other set. Okay, so this first example says, which of the following sets are equal? Well, they're only equal if they have the exact same numbers in them or the exact same letters in them. So let's see, I have a BHJK and I have another BHJK in the C. So those two suckers are equal. It's okay that they're out of order, but both of them have a B, both of them have an H, a J, a K. Both of them have 4 things inside. So A is equal to C. Okay, another thing is, over here on the left, this 0 with the slash through it, and just an empty set of squiggles, both mean the set with nothing inside. As in, there's not an A or B or C. There's not a 1, 2, 3 inside these squiggles. It's just nothing. So, since both of those mean nothing inside the squiggles, they're equal. So let's find them. That will be H and 0 with the slash through it. Okay. This G, if you're wondering, what does that G mean? It means instead of like 0, 1, 2 in the list, it's just the number 0 in the list. So that does not equal H or E, because E and H both have nothing in the list. So E and H are correct. And then let's see here. This one with the 0 inside just means it has a 0 inside. F is just bad typing. It's a bad format. You can't put that 0 with the slash through it inside squiggles. Okay, this D says the numbers have to be in between 2 and 5, and they have to be capital N. That means like counting numbers, how we count with our fingers. So this set just means 2, 3, 5. Oops, I mean 2, 3, 4, 5. All the numbers in between 2 and 5. Okay, let's look at this. This means all the numbers where you multiply by 2 and add 3. So let's say I plug in 0. 2 times, oh, and for this 2n plus 3, n is an element of a W. That means the whole numbers and 0. 0, 1, 2, 3, 4. On the next one, it says n is an element of capital N. That just means the finger counting. 1, 2, 3, 4, 5, blah, blah, blah. Okay, so for this first sucker, let's plug in a 0, 1, 2, 3. And we get 3, 5, and 7, I think. But then let's compare it to this 2n minus 3. And this time we're only plugging in 1, 2, and 3. So for this first one, we get 5. The second one, we get 7. The next one we get 9. So the point is, we were trying to find out whether things are equal. So A and C were equal because the exact same things were inside the squiggles, just different orders. For this 2n plus 3, we found out that inside is 3, 5, 7, but it keeps going. I can keep plugging in numbers forever and ever and ever and ever and ever. So this 2n plus 3 is going to have 3, 5, 7, 9, 11, dot, 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 dot. And this 2 and minus 3 is going to have 3, 7, 9, dot, 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 forever and ever and ever. So the question is, are any of these equal? Is this 2, 3, 4, 5 the same as 3, 5, 7, 9, 11? Nope. Is this 3, 5, 7, 9, 11 the same thing as 3, 7, 9? Nope, because I'm missing like a 5. So these are not equal. This pink and this blue are not equal. So the whole point was to find equal sets. Well, we only found 2 pairs. The ones with the common letters and the weird empty squiggle and the 0 with the slash through it. Okay, let's keep going. The next thing we're gonna do is find the cardinal number. The cardinal number is the number of things inside a set. So for example, let's say we have the set of numbers for 3, 4, 5, 6, all the way to 12. To find the cardinal number, you take the last 12 minus the first 3. And then you add 1. Always add 1. And that gives me 9 plus 1, 10. So that means in between 3 and 12, there should be 10 numbers. Let's see, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yee! Okay, let's look at the next one. The next one, it's from 2 to 10, but look at what the numbers are different by. They're different by 2. See how they go up by 2, 2, 4, 6, 8. That's not how this first one went up. This first one went up by 1. Okay, for this sucker, you do the last minus the first. Then you divide by 2 because each number in the list is 2 more than the previous. Then you add 1. Okay, so let's do this. We're going to say last minus the first. 10 minus 2 is 8. Then we're going to divide by 2. 8 divided by 2 is 4. Then we're going to add 1. 4 plus 1 is 5. So there should be 5 numbers in the list from 2 to 10. Counting by evens. Let's see. 2, 4, 6, 8, 10. How many numbers are those? 1, 2, 3, 4, 5. Yeah. Okay, sometimes the numbers are freakishly big and it's easier to use these tricks of last minus first plus 1 or last minus first divided by 2 plus 1. And then sometimes it's easier if you just count with your fingers yourself. It just depends. Okay, let's look at this example. Part A, it says find the cardinal number. And it says from 220 to 819. Well, I don't think I'm going to list out all these numbers and count with my fingers because I don't have enough fingers. So I think I'm just going to do the whole trick thing. And either these numbers go up by 1 or by something else. And they all go up by 1. So I'm going to use that first trick of last minus the first plus 1. So for part A, we're going to have 819 minus the first 220 plus a 1. And I got 600. So that means there's 600 numbers in between or in this list from 220 to 819. Okay, let's look at part B. Okay, it looks like these numbers are going up by 2. So that means I'm going to have to use this second trick of last minus the first, 126 minus 8, and that gives me 118. Then you have to divide by 2 because each number in the list is 2 more than the previous. So 118 divided by 2 is 59. Then you add 1. 59 plus 1 is 60. So there should be 60 numbers in this list from 8 to 126. Okay, let's look at part C. Part C is a little awkward, but over here it said for part C and D, you just count using your fingers. Okay, well, let's see here. For part C, what does it look like is happening? It doesn't look like we're adding the same number, because from 9 to 18, we add 9. Then from 18 to 36, we add 18. Oh my gosh. So for part C, we can't use a trick. We can only use that trick if the numbers are different by 1 every time, or they're different by 2 every time, or they're different by the same number every time. These are not different by the same number every time. We add 9, then we add 18, then we add 36. It's not the same, bro. Okay, so for that, we're just gonna have to list them out, okay? And count. So we got 9, 18, 36, 72, 144. And let's think about this. Instead of adding, what are these numbers doing like multiplication wise? To get from 9 to 18, you multiply by 2. And from 18 to 36, you multiply by 2. And from 36 to 72, you multiply by 2. Okay, well, let's keep going in our list to come up with all the rest of the numbers all the way to 4608. So we do 144 times 2 is 288. Times 2 is 576. Times 2 is 1152. Then 2304. Then 4608. Okay, and the whole point of this is we were supposed to find the cardinal number, as in how many numbers are in the list. Well, we couldn't use those tricks from part A and B because we could not add the same number over and over and over. So instead, we just figured out what number we had to multiply by, and we found all the numbers in the list. And then now let's count using our fingers and toes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. There are 10 numbers in that list. Okay, let's go to part D. D says for K equals 1, 2, 3, 103. Okay. Well, how many numbers are in the list from 1 to 103? I think that's kind of easy. From 1 to 103, there's 103 numbers in the list. So that one was super easy. Part C, we had to figure out what the numbers were changing by, and we had to come up with more numbers in the list, and then we counted. Part A and B, we just had to use a little trick. Okay, the next thing we're talking about is how to count up how many elements are in a subset or a proper subset. So we know how to find how many elements in a set. That's what we just did. You either use the trick of last minus first plus 1, or last minus first divided by the number that they're apart plus 1, or we just had to use our brain and we had to figure out the rest of the numbers in the sequence and count up. So that's how many elements are in a set. Now we want to know how to figure out how many elements are in a subset. Well, to figure out how many elements are in a subset, we use 2 to the n formula. So part A over here says, how many subsets does A have? Well, we have 2, and then we have to count how many letters were up in here. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 total numbers. So we'll say 2 to the 9th. And then we put that in the calculator. And make sure you use that caret button or that up button above the divide. and I get 512. So that means there's 512 different combinations I could make up of these 9 letters. They could be out of order, they could be unalphabetical, but I would come up with 512 combinations. Okay, now for proper subsets, the formula says 2n minus 1. Okay, well, part B says something about proper subsets. So I say 2 to the n minus 1. Well, we already did that. 2 to the n was 512. So I'm just going to say 512 minus 1. And that's 511. So subsets, there's 512 possibilities. Proper subsets, 511. Then part C says, how many subsets does A have that includes the elements of A and I? Okay, so to do that, we use this last equation. It says subsets that include the elements. Looks like this formula, 2 to the n minus the number of elements you're looking for. So our formula is going to be 2 to the n minus the number of elements you're looking for. So 2 to the, what's our n? Our n is 9, because there's 9 total letters. And then minus, how many elements are we looking for? Let's check. We're looking for A and I. That's 2 elements that I'm looking for. So I'm going to subtract 2 in the air. So that gives us 2 to the 9 minus 2 is 7. And then we put that in the calculator. 128. So there are 128 of these 512 combinations that it'll involve A and I. Okay, let's look at the next one. This next word that we're going to learn is well-defined. It says, a set is well-defined if any given subject can be classified as belonging to the set or not belonging to the set. And the key in the definition is well-defined. In a second, we're going to see some words that are not well-defined. As in, if anything is biased, it's not well-defined. And when I say biased, I mean if it uses opinionated words. Like, he's a great guy, or this is the best thing ever. You know, great, best, things that don't really measure accurately with numbers. That would be something that's not well defined. So let's look at this. It says, which of the following sets are not well defined? Part A says the set of rich musicians. Well, that's not well defined because we don't know how rich. We don't know the amount of money. So this is just an opinion. Whoever makes up this set is going to use their opinion of rich musicians to include them, but that's not well defined. We need it to say the musicians making above $1 million. So this is not well defined. Part B, the set of important paintings. Who determines whether something is important or not? Because a mother of 5 probably thinks that all of her children's artwork is important, but maybe some snob thinks that Picasso is important. So this important is not well defined. Part C says the set of whole numbers greater than or equal to 145. That's well defined because it's all the whole numbers bigger than or equal to 145, as in they gave us a number. So part C is well defined. D says the set of subsets with the numbers 1, 2, 3, 4. Again, they gave us numbers. It's well defined. Part E is a little trickier. They gave us an equation. So opinionated words are out, like rich and important. Equations or numbers numbers are in, like 145 and 1234. Equations, we kind of have to think about this for the equation. Let's say we have this x alligator x minus 1. And let's say we plug in the number 5 for x. Let's see if this comes true. Over here on the left, we have 5, then alligator, 5 minus 1. Well, 5 minus 1 is, what is it? 4. And is that true? Is this alligator eating the bigger number? And the answer is no, it's not. This is wrong. 5 is not smaller than 4. So E is not well defined. So A and B were not well defined because they had opinionated words. Part E was not well defined because when I plugged in a number, I saw, wait a minute, the alligator's backwards. Okay, we're gonna go ahead and stop.